So what does this video show? This video simply shows us a light bulb. Like I was explaining to you, the light bulb which has that small filament of tungsten inside, which basically gets heated up and emits light. Okay. Now, this small animated GIF just shows to you what I told you. Like when you switch on the light, can you see inside the glass of the bulb, there is this wire that is going like round and round in like a spring or a spiral. That is the filament of the light bulb, or usually which is the material of tungsten, and that tungsten gets heated up because it has a very high resistance, but because it has a very high melting point also, it gets heated up but it does not melt and it emits light. Okay, now let's just quickly just read what your PPT says here. Okay, so it says that a strong metal with high melting point such as tungsten is used for making bulb filaments. So why is tungsten used? If you are asked what is the reason for tungsten to be used, the reason is that it has high, MP means high melting point. Then it says most of the power is consumed by the filament and appears as heat, but a small part is radiated in the form of light. So that's what I told you. The energy that is expended by the battery to maintain that potential difference across the circuit is used up in the form of either to rotate the fan, if there is something like that to be rotated or moved. Otherwise, it is expended in the form of heat and light. And when the resistor gets to a very high temperature, it emits light. And apart from high melting point, it has a high resistance also. Okay, great. Let's move on now. So now we're going to study the electric fuse and its working. So let's just read in your PPT once and then we'll explain. So it says that the electric fuse protects circuits and appliances by stopping the flow of any unduly high electric current. We'll explain this, just read it once. It must be placed in series with the device, consists of a piece of wire made of a metal or an alloy of appropriate melting point, for example, aluminium, copper, iron, lead, etc. Okay. So what does this exactly mean? Why is an electric fuse required? So we know that current normally flows in any circuit, right? But just think about the practical use. Like in a practical situation, say when current is coming into your building appliances, like your whole building has some wire connections for different appliances and different places, like your electric bulbs or electric tube lights which are there in your house, all of that requires current, right? So say any device requires only a specific amount of current, right? So for an example, if I have to give you an example, say I have an electric iron. Okay, an electric iron which uses up, or which how much power it uses is 1000 watts when it is operated at 220 volts. So we have power and we have voltage. So can I find the current here? Yes, we know P equal to V into I. So therefore our I is nothing but P upon V, which is 1000 upon 220. So this becomes 11 and this becomes 50. So this approximately becomes 11 fours are 44. So 6, around 4.5 amperes, right? So basically this electric iron or whatever appliance this is uses 1000 watts of power and it is operated at a 220 volt source. So using our formula, we have seen how much current does it require? It requires only 4.5 amperes of current. Now just think. So just think that this appliance is at your house. Now, where is the current coming from to your house? It is coming from some electric, like you pay the electricity bill to some agency or some organization which sends you power, right? So for whatever reason, suppose there is a hike in the current that flows. It is physical, it is a physical thing. It can like fluctuate, right? Current can fluctuate even if a constant potential difference is being provided at the source, there might be, because of any reason, that the current suddenly fluctuates. So say if this iron heater or electric heater just requires 4.5 ampere and suddenly 8 amperes of current flows through it. Do you think it would be able to take in that 8 amperes of current when it just requires the 4.5 ampere? No. What it will do is that current will actually damage your electrical appliances, right? So this is the reason an electrical fuse is needed. So what does a fuse exactly do? Say if this appliance needs just 4.5 amperes to operate. So what a fuse does is, it takes like a small margin. Say 4.5 amperes is needed, even if say after a hike a current of 5 ampere comes into the wire. Even then the material is not going to get affected. It is going to get affected when it goes to like 6 ampere, 7 ampere, 8 amperes, like that much difference in the current that is required to the current that actually comes is there. So to a 5 ampere current there is not much of a difference. So we put a fuse which actually breaks when a current more than 5 ampere comes into the circuit. Okay, so what is the purpose of the fuse? The fuse is basically, it acts like a protector for that circuit which detects or which breaks itself when a greater current than required flows through it. Okay, that is the basic use of the fuse. And in this case, I will say that we use a 5 ampere fuse in this circuit. What does that mean? That means that as soon as a current greater than 5 ampere is going to come into the circuit, that fuse will break. And what will happen? What is given here? It says that the fuse must be connected in series with the device. So what happens? Say this is the fuse, right? And this is your electric heater or iron or anything. I'm just representing it with the bulb sign. This can be anything. Let's represent it as an X. So this is your device and it is connected in series. So let's say this is the electric iron that I took an example of. So say a current of 4.3 amperes is coming. Would it affect this? Would it affect my iron? It won't, right? Because my iron needs at least 4.5 amperes. So 4.3 ampere current will not like affect my electric iron, or it would not damage my electric iron. But say a current of 7 ampere comes. Is that good for my appliance? Is it good for my device? No, it would cause some damage to my device. So I don't want that current to pass through my device. So that is why I put a fuse in series with my device. So what does the fuse do? It detects as soon as the 7 ampere current goes through this fuse, it breaks. So what happens when this fuse breaks? This circuit becomes open like this. So can this 7 ampere current reach my device now? No, right? Just think, if this fuse wasn't there, what would have happened? This 7 ampere current would have gone into my device and it would have damaged my device. Then I would have incurred a loss. Then whoever the electrician comes, he would have to replace that material completely, right? But in case of a fuse, it's just a small piece of, say, aluminium, copper, the examples that are given to you. So all the electrician has to do is just come and replace that small piece of wire or the small piece of fuse. So there is no damage that is actually done to your appliance or your device. Okay, so I hope the concept of fuse is clear to you now. The fuse basically breaks the circuit to protect your appliances from an unduly high electric current. What does unduly mean? That it is not supposed to actually happen. It is not planned for. It just happens due to some reason. There is a hike in the current. Okay, great. Let's move on. So it says that if a current larger than the specified value, like in the last question, we saw that 4.5 amperes was the current that was required by my heater. So I put like a 5 ampere fuse, which means I am giving like a margin of around 0.5 amperes, because a 0.5 ampere increase in the current is not going to damage my device as much. But a 1, 2, 3 ampere current is going to damage my device. So I take this small 0.5 margin and take a 5 ampere fuse which I connect in series with my appliance, which was my electric heater or iron or whatever I want. Okay, so if a current more than this value of the fuse, the current that the fuse can take if a current more than that comes into the fuse, it breaks and it breaks the circuit. Why is it connected in series? Did anyone think about that? Say this is our fuse and it is connected in parallel to my appliance. If this is my appliance X, so what will happen? If a 7 ampere current comes from here, it how would the fuse break the circuit? If it goes from here, the fuse might break. Okay, even if the fuse breaks, the current has a different path to go from, so it would still go through my appliance and still damage it. So that's why in this case, in case of fuse, we always connect it in series with the appliance that we want to protect from an unduly high current. Okay, now it says that the specified value flows through the circuit. If a current larger than the specified value flows, the temperature of the fuse wire increases and it melts the fuse. So would we need a high melting point wire for this or low melting point wire for this? We need a low melting point wire, because if a wire doesn't even break at very high values, then it would let large currents flow through it and it would damage the device. If it is a low melting point wire, then as soon as a little extra current flows through it, it gets heated, and because the melting point is less, it gets melted. Okay, so that is how the fuse actually works. Now, electric power, we've already talked about this, that it is the rate at which energy is dissipated or consumed in an electric circuit. Like we wrote, power is work upon time, or as work and energy are equivalent, we write power is equal to energy upon time. Okay, now here we knew that we derived the formula P equal to VI, right? We did the derivation before. I'm not going to do it all over again. And then using Ohm's law, we replaced, in place of V, we put V equal to IR. So I put P equal to, in place of V, I put I into R into I. So what does this become? It becomes I square R. So this is a new formula for you, that power is I square R, right? I square RT, what was I square RT? That was heat, which was the heat produced, right? I've done the derivation there completely for you. You can go back and check it if you don't remember. So P is equal to I square R is one new formula for you. Again, if P equal to VI, last time I replaced V by IR. This time, if I want to replace this I in V equal to IR, what is I? I is equal to V by R. So in this formula, I put V by R in place of I. So what does it become? P equal to V into, in place of I, V by R. So what does this become? P equal to V square by R. So these are the two new formulas, 1 and 2. These are the two new formulas for power. Okay. And the SI unit of power is watt. We already know that. 1 watt is the power consumed by a device that carries 1 ampere of current, which operates at a potential difference of 1 volt. How did we come up with that? We use P equal to VI, and as you know, to get 1 unit of anything that we want to define, we take everything else as 1. So we take V as 1, we take I as 1. So power comes out to be 1 only, 1 into 1. So what does the definition say? That 1 watt of power is the power consumed by a device that carries 1 ampere of current and works at a potential difference of 1 volt. Okay, so I'm sure you should be confident with defining the terms like this by now. Okay, moving on. So here it says the commercial unit of electric energy is actually kilowatt hour. Why is it kilowatt? Because actually 1 watt is a very, very, very small value. So in practical purposes, we actually deal with 1000 watts, and this 1000 can be replaced by kilo. So it is 1 kilowatt. So 1000 watts is nothing but 1 kilowatts. Okay, this is the representation that we use. Like millisecond is divided by 1000. Like that, kilo is multiplied by 1000. Okay, sorry, millisecond is, yeah, it is divided by 1000 only. I was saying correctly. Okay. Now, how is it kilowatt hour? We know that energy is equal to we know that power is equal to work upon time, right? And actually work is nothing but energy. So now here I'm not talking about the energy in joules where we are doing some work as humans or something like that. I'm talking in terms of electrical energy. So here energy is what? P into T, and T is what? Watts. The unit of power is watts. And if we take the unit of time as hours, in commercial purposes we use it in hours. So the energy unit actually comes out to be watt hours. Watt into hours. Okay. So the commercial unit of energy is kilowatt hour. So here it's watt hours, and in the beginning I told you that this kilowatt is the standard unit that we use. So it's not actually just watts. So energy is also written as kilowatt hour. So if you see this representation anywhere, don't get confused. This is a small k. Okay, this is kilowatt hour, which is commonly known as unit. So one unit of electrical energy, if it's written 1 unit of electrical energy, you should automatically know that it's kilowatt hour of electrical energy. So here you have the conversion. 1 kilowatt hour is nothing but, I told you that 1000 watts is 1 kilowatt. So in place of kilowatt, they've written 1000 watts. And if you remember, we did the conversion of hour to second, so it's actually 3600 seconds. So we simply multiply this and we get 3.6 into 10 to the power 6 watt second, which is joule. Okay, this is a derivation that you should be clear about. Okay. Now, about the electric bill. So you must have heard, sometime you must have heard one of your parents say that switch off the fan when you leave the room, or switch off the light, or switch off the AC. And although that is also for environmental purposes, to save our environment, it is also because if you leave your fans and lights and ACs on for a long time, your electrical bill will come out to be very large, right? So you basically, like I said, that some organization or some source provides you with the electricity to run all the appliances in your house. Why would they do it for free, right? So they charge us some amount based on how much we consume. So the electrical bill is basically based on how much energy or electrical power we consume. So here it says that we pay the electricity board or electricity company to provide energy to move electrons through the electric gadgets. What does moving of electrons or electric charge mean? For current, right? The current is the thing that actually runs all of our devices, right? So we are basically paying them for giving us current or current electricity through electric gadgets like our light bulbs, fans, engines, heaters, irons, etc., etc. So basically we pay them for the energy that we use. Okay? Great. Moving on. So here we have a question that says an electric bulb is connected to a 220 volt generator and the current is 0.5 ampere. What is the power? Okay, we follow our basic steps which we always write the given. What is given to us here? We are given that the source or source voltage, we are given voltage or V is equal to 220 volts, right? Then we are given that the current I is equal to 0.5 amperes, and we are given the power P is equal to, is something that we have to find. So can you think of any formula that has V, I and P? I can think of a formula, but can you? Just think about it. You've used this formula a few times now. So in the answer we write using P equal to VI. Okay, now you have to start recalling and remembering these formulas because you've already derived it. So you know the logic behind it, but now you have to have these formulas on your fingertips to be able to solve numericals. Okay, so we simply have to do P equal to voltage into current, 220 into 0.5. So this 0 is used in removing this decimal. 5 2s are 10, 5 2s are 10 and 11. So 110 watts is our answer. So you just write one line here that 110 watts is the power of the bulb. Okay, moving on. So the question says that an electric refrigerator rated at 400 watts, what is this 400 watts? This is the power, operates 8 hours a day. Okay, this is the time. What is the cost of the energy to operate it for 30 days at 3 kilowatts, 3 rupees per kilowatt hour? Now this is a practical purpose question because it uses kilowatt hour, which is the standard unit which is used by our electricity bill boards also. Okay, so again, as I have told you a lot of times, it is my humble request to you, please don't look at the question and be like, oh, this looks like a very tough question, because you'll just be telling your mind that it's a difficult question and you won't be able to do it even if you know the concepts. Okay, so whenever you look at the question, follow the simple system that I have told you. Write down the given things, think about what you know, and apply the concepts that you have learned, and you will reach the answer slowly, step by step, and with practice. Okay, so I'm going to do what I always do. I'm going to write what is given to us. We are given that the power for the power P is given to us as 400 watts. Okay, it operates at 8 hours in a day. So I'm writing in 1 day how much time T. It is 8 hours. Now, do you think I should convert it to seconds? Should I convert hour to seconds? No. We usually do, because that is the standard unit in normal questions. But look at this. Look at the 3 rupees per kilowatt hour. In the final answer also, it is in terms of hours. Like I said in the last slide, that the standard unit is kilowatt hours, which is known as 1 unit. So in practical purpose questions like these, we do not convert the hours into seconds, and this should be your biggest hint, that here it clearly says hours, so the final answer has to be in hours only. So we leave it like this. We have the time. What is the cost of the energy to operate it for 30 days at 3 rupees per kilowatt hour? Okay, so we have to find cost, to operate for 30 days at 3 rupees per kilowatt hour, right? This is what we have. Okay, so now we'll go step by step. I have the power, I have the time, and what do I need to find here? I need to find the cost of the energy to operate it for 30 days at 3 rupees per kilowatt hour. So I need to find it for 30 days. So can I first find it for 1 day, right? That's what we always do. You remember when we did unitary method, you always found out whatever the cost or whatever it is for one, and then you find it out for multiple, right? So let me find out how much power it actually spends in 1 day. Okay, so how will I find it out? Power used in 1 day. If I want to calculate that, I have power it uses and I have the hours it operates for in 1 day. So simply the power it uses into number of hours that it operates for would give me the total amount of power that is used in 1 day, obviously. So I write P dash. This is the total power used in 1 day. That's why I'm representing it by P dash. So what does this give me? 8 ones are 8, 8 twos are 16, 8 threes are 24, 8 fours are 32. So this is 3200 watts, right? Great. Now this is given to me for 1 day. Now what do I have to calculate? I have to calculate the cost of the energy to operate it for 30 days. Now don't get confused because it says energy here but we only have power and time. Why? Because look here, this kilowatt hour is in the unit of energy. Yes, but this now, sorry, this is actually not power, energy. This is energy. This is energy used in 1 day because we are doing, that is why you should just write the units also here. So this is 400 watts into 8 hours, right? So what does this become? 3200 watt hours. And what was the unit for energy? It was nothing but watt hours or kilowatt hours. We'll change it to kilowatt hours, but the basic unit we have got right for energy, right? So it has asked me what is the cost of the energy to operate it, and I already have the energy here, but this is the energy used in 1 day. Now I have to find the energy used in 30 days. So what do? I have it for 1. I multiply it by 30 simply and I get the energy used in 30 days. Okay. So energy in 30 days, used in 30 days, write the whole sentence is E dash, this is the 30-day energy, is equal to this 1 day energy, which is 3200 watt hours into 30. 1 day ka energy into 30 gives me 30-day energy. So what does this become? 3 2s are 6, 3 3s are 9, 96, 1 2 3, 3 zeros. This is still watt hour. But if you look at the money, it is given to me per kilowatt hour. So that should tell me that I need the energy in kilowatt hour only. So what do? This is 96,000 watt hours, and I told you that the 1000 is 1 kilowatt. 1000 watts is 1 kilowatt. So 96,000, this 1000, this 3 zeros is replaced by K or the kilowatt. So what does this become? The new energy, which is the energy for 30 days, is 96. So our decimal is actually here. So it goes 1, 2, 3 places back. It goes here. So 96 kilowatt hour. Now we have the unit which actually is used in the money unit that we have here. 3 rupees per kilowatt hour. Great. Now we have 96 kilowatt hours for 1 month. So simply, what is the concept we use for calculating the cost? If 3 rupees is for 1 kilowatt hour, then for 96 kilowatt hour, how much cost will it be? 3 rupees for 1 kilowatt hour. So for 96 kilowatt hour, it would be nothing but 96 kilowatt hour into 3, which is 6 1s are 6, 6 4 1s are 18, 9, 18, 27, 28. So it is nothing but 288 rupees. Okay, the question might have seemed a little difficult, but when you go step by step and apply your logic and knowledge, you get to the answer easily. Okay, moving on. Now this question says, what determines the rate at which energy is delivered by a current? Now, look at it carefully. What is it asking? Is it asking just about the energy? Is it asking just about the energy? No, it's asking the rate at which energy is delivered. So, just think about it. What does rate mean? Rate is always division by time. And what is energy by time or work by time? It is nothing but power. So, it might seem like this question is asking about energy, but it's not actually asking about energy. It's asking about the rate at which energy is delivered, which is power. So, we know that, we'll write that. We know that power is V into I, or power, by replacing V by IR, it is I square R, or by replacing this I by V by R, it is V square by R. So in all these three formulas, we can get to know what are the variables or symbols that the P is depending upon on V, I and R. So you simply write that power depends upon, power or energy, at the rate at which energy is delivered, you write both the things, depends upon the potential difference of the circuit, current through the circuit and total resistance in the circuit. These three things. Okay, great. Now, the next question says that an electric motor takes 5 ampere, this is the current, from a 220 volt line, this is the voltage or potential difference. So, determine the power of the motor and the energy consumed in 2 hours. Okay. So, what do we have here? We have current I is equal to 5 amperes, and then we have voltage V is equal to 220 volts, right? Now, what do we have to determine? Power. Simply, we know P equal to VI. So, P is equal to V, which is 220 into I, which is 5. So we know 5 2s are 10, 5 2s are 10, 11 and a 0. So it is 1100 watts. Now the next part says that and the energy consumed in 2 hours, right? So now think about it. We have power and we have time also. Time is given to us. We have P and we have T. Can we find energy from here? Obviously, we know that power is nothing but work upon time, or if we replace this work by energy, it is energy upon time. So what is energy? It is nothing but power into time. So power is nothing but 1100 watts. So this is our energy. 1100 watts into time is given to us as 2 hours, right? So I'm not converting this to seconds because I want it in the standard unit. So this becomes 2 ones are 2, 2 ones are 2, 100. So if I want it in kilowatt hours, this is in watt hours. So if I want it in kilowatt hours, I take the decimal back 1, 2 and 3, right? So this becomes, the energy becomes 2.2 kilowatt hours. This is the energy which is consumed in 2 hours, okay? Okay students, so this was it for our chapter on current electricity. I hope all of the topics are clear to you because we have done some very important practical topics in this chapter also. So make sure that you are thorough with all of these topics. In the next chapter, in the next video, we're just going to do a quick revision of it so that all the small concepts are just brushed up in your mind and it is fresh in your mind before you start doing numericals on your own. Okay students, I hope you enjoyed this lecture. Thank you so much and take care.